Hello guys, so today I have lectures in differential geometry by Shlomo Sternberg for you. And um, this tour is kind of um, going to try to bridge conceptually what's happening in this book. Um, why this, most differential geometry books are going to have some kind of computational, index gymnastics, if you know what I mean, Christoffel symbols, and try to define, just like local transformations right at the get-go, and just emphasize those coordinate type of techniques. But what I like about Sternberg is he teaches how to think about invariant geometric structures, and coordinates themselves are going to be like these, these shadows, if you will. You'll start thinking about coordinates in this way. Um, of course, this book is going to assume knowledge of um, basic modern algebra that a book like Shilov would prepare you adequately for. Um, Shilov's linear algebra. Um, but yeah, and he provides some nice. Sorry about the rendering. Um, he provides some nice a nice preliminary, but really he's going to teach us um, how to think about these true geometric objects that coordinates kind of obscure. So the idea of like derivations, differential forms, vector fields, connections, curvature. This is a very conceptual book, and that is part of what this book is trying to, or what it achieves, what it actively achieves. Um, so differential geometry in Sternberg's hands is not primarily about curves and surfaces in some random ambient space. You can think of it as more of a systematic study of invariant structures on smooth manifolds. So, you kind of replace this notion of a coordinate dependent intuition with, something that you would get out of like a physics text, like Landau and Lifshitz, volume 2, where, you start with the computational necessity of describing, things like space-time intervals or electromagnetic fields. So really, you would want to supplement this book with some physics as well to ground it. But nevertheless, this book will study the geometric objects themselves that are independent, that are coordinate-free concepts to get the absolute mathematical language that underlies pretty much all of theoretical physics and modern math. So, um, he starts off, I guess, these first two chapters with thinking about like uh, just thinking about space, right? What is the geometric space when you decide to challenge the notion of global flatness? Okay, so that's really what these two chapters are created for, is to identify what space is essentially, what space is in the geometric sense, and then integral calculus on manifolds. Really, we want to know how do we decide to measure volumes or fluxes through surfaces um, and orientations in such a way that is invariant. And you can think about motion as well as defining the calculus of variations um, to give us the idea of and also Lie groups as well. Lie groups are important for motion because geometry itself is going to evolve through flows or variations or even the symmetries themselves. It gives us the evolution of the geometry. For example, um, if you took like a rigid rotor, right, and you wanted to describe um, a rotating black hole, if you will, in space time, that of course space time is torsion free. So that particular um, solution to the Einstein field equations um, would necessitate some perspective from differential geometry, right? And you also have the differential geometry of Euclidean space, and the geometry of G structures. These are more about just measuring curvature in general, and curvature is the prelude to understanding gravitation, or vice versa. Gravitation um, is the prelude for the mathematical notion of curvature, which basically says what prevents a space from being flat, and how is that obstruction itself measured in a more general sense. So these arcs, through the chapters are not really they're not isolated. They're gonna build, previously just as any other book would. I think there was like a layout on like you know which chapters belong to which. I don't remember if it's on this book or not. Sorry, I've been looking up other books, but I'm barely kind of haven't like super reviewed this, so you'll have to bear with me. But as I find things, but yeah, we just start from regular the algebra of tensors and space geometric notions to full Riemannian geometry. So it's just a very um, this book is pretty kaleidoscopic in that sense. So Sternberg, he's going to assume mastery of algebraic language of vector spaces operators. Okay, and you're gonna have to know you're gonna have to have read a pretty good linear algebra text to be prepared for it. But then he's going to distribute that language, across some curved spaces. Um, you know, every curve being infinitesimally straight. Um, the differential map is infinitesimally linear. So you first study the idea of differentiable objects that then you will fall under the heading of what is known as multilinear algebra. So we're going to build, the idea of curved spaces based off of the fact that, up locally we get linear behavior. And the resulting geometric structures, like symplectic forms or connections and curvature, you can think of these as like naturally the mathematical scaffolding for the physics of analytical mechanics, gauge theories. So physics is going to emerge as a direct consequence of the geometry that we study. So um, yeah, again, the main idea of differential geometry is to apply the tools of analysis to the solution of geometrical problems, and of course, it's to study them uh, or to basically to take crucial advantage of the fact that um, the crucial advantage is that the infinitesimal linearizes everything. So, um, I guess the question you should ask yourself reading this is what algebraic structures survive when coordinates disappear entirely. So, um, he defines a tensor product or vector spaces and dual spaces, um, and goes through the notions. I'm not gonna like hold your hand through everything, but you can read. Um, but yeah, and then he'll define in vector spaces there exist multilinear maps, um, tensor algebra of a vector space. Um, then he'll go into the exterior algebra later. I think. Let's see. Exterior. Sorry, the PDF is pretty slow, so you'll have to bear with me. But the exterior algebra um, looks like some, wedge P of a vector space, um, or of, whatever arbitrary way that we choose to represent it. But we have the alternating multilinear form as well that we would want to define, and determinants and orientation. But you can basically what's interesting about exterior algebras. I mean, I don't really want to go super um, be super dramatic about it, but the dimension theorem. I would say probably the dimension theorem is pretty nice result. Which is that the dimension of let's find it. and it has to do with the in choose k and the linear dependence of vectors being equivalent to the non-vanishing of their wedge product. It's also something to note. Um, where interior multiplication. Hmm. But yeah, exterior equations. Yeah, I mean, really, what how to think about everything is that every nonlinear geometric object is going to linearize at this infinitesimal level, so your local geometry is therefore going to be governed by multilinear algebra. The exterior algebra is going to provide you essentially, basically, uh, it's going to provide you the language for defining volumes and geometric orientations and integration that will be needed globally later in the chapters. And determinants are going to be these intrinsic volume forms. And you can think of alternation itself as like orientation. And linear algebra is going to cease to be some, just topic that, becomes the local grammar for all the subsequent geometry. This chapter here is going to mature the concept of vector spaces pretty much. I mean, that's really all that there is. Duality um, is a topic as well. Multilinear algebra in a coordinate-free maturity that would be ready to be attached smoothly at every point of a manifold. So a nice exercise would be to show the identification of a vector space with its dual, or the dual of the dual of a vector space. The I guess that isomorphism would probably be one of the most important things to walk away with as well. Just because the object and its measurement belong to a single symmetric structure, and you know this returns as cotangent bundles, differential forms, metric duality. So you want to make sure that you understand those things as you go through. Um, and of course, he's giving you a survey of the landscape, of like ideals and properties of these algebraic, uh, of these exterior algebraic um, type of properties as well. So it's very nice. But let's move on to chapter 2. Um, so basically, this is about. I mean, I would say the central question of this. The central question of this chapter that it seeks to answer is what direction or velocity, if you will, on a space where global coordinates um, and straight lines. What is some direction where the straight lines don't exist, basically? Um, or velocity. So you can think about like differential manifolds, charts, atlases, tangent spaces. Let's find the definition of a tangent space because I like his definitions. Um, let's see, tangent space. Yeah. So tangent space. In our study of differential manifolds, to introduce various. We will give a treatment of such objects in the next section. In order to motivate treatment, we first study the notion of a tangent vector on a manifold. Um, a tangent vector is curved to a curve is straightforward. We have a vector valued parameterization of this. Um, Now he tries to define on manifolds. We can't write every curve as an intuplet of functions. So what they do is, in a more abstract way, they find an equivalence class of curves through a point, or P, and two curves being the same derivatives as one, local coordinate systems about P. So now the reason why you would want to do this is because tangent vectors are going to be are going to be derivations. So they would be canonically isomorphic to the space of derivations on continuous manifolds at P. on the space of continuous maps at P. So you can think about these again with differential manifolds, charts, atlases that define, how we're choosing to um, globally obstruct the space, if you will, from a local perspective. Um, we essentially, the geometric meaning is that direction itself is a differentiation. So the um, motion is going to be this infinitesimal action on functions, and the coordinates will become secondary types of local labels. So yeah, I even highlighted this earlier. But a tangent vector on a manifold corresponds to a unique linear function. Oh, so yeah, this is a nice one. So this gives us the property of derivation itself, because what's nice about this is linear operators and change of basis transformations. The change of basis transformations will allow us to really think about how it's linear independent of h. So it'll allow us to define these objects in a more abstract functional type of way. And basically this derivation property allows us to answer that initial question was, what is the direction on the space where the global coordinates and straight lines do not exist? So and the answer to that, which would just be the fact that direction is differentiation itself. And differentiation is this type of operation here, all right? A unique linear function. So that's a nice theorem here. Now, Lie brackets. I think Lie brackets get talked about in this chapter as well. That's what my notes say. The Lie bracket, I think, gets first. Yeah, here we go. Introduced here. So this allows us to do is just define really the Lie bracket of vector fields allows us to then define, I guess, the non-commutivity. It allows us to introduce the non-commutivity of flows of a vector field. And what that teaches is that the failure of two motions to commute, if you will, if they're not anti-commutative, but if the failure to commute in general carries an essential geometric information about the space itself. And so he's planting seeds, if you will, of Hamiltonian mechanics, Poisson brackets, Lie algebras, all of these types of more algebraic structures that we get in quantum mechanics. They underlie the symmetries themselves in the quantum commutators. So that's the importance here. Now, I accidentally just went back to. Let's go ahead and go to the next chapter. It's called Integral Calculus on Manifolds. All right. Yeah, so integral calculus on manifolds. This chapter study of analysis of manifolds. So, I mean, the reason we'd want to even integrate anything in the first place is to perform measurement, right? And what we're going to ultimately try to do is perform measurement on curved surfaces or curved spaces without coordinates. Coordinates themselves kind of disappear when we start to introduce the language of differential forms and the exterior derivative. So that'll get defined here. And then, of course, in general, we'd like to have an equation. So something that would allow us to create Stokes' theorem. Differential forms, integration on chains and manifolds, de Rham cohomology. These are all things that get kind of covered in this. Let's look at first Poincaré's lemma, because I know that's in this chapter. Poincaré. Yeah, so Poincaré's lemma basically tells us that closed forms are locally exact. Basically, right? Locally, This is defined on a ball. Um, Now, the reason why you would want to do this, or the reason why this is an important thing, is because it allows us to then, knowing that closed forms are locally exact forms, um, which preluded from the differential or from the variational or from the integrals themselves that were used to solve these types of exact differential equations. Um, the Also the Frobenius theorem. Let's go. Oh well, okay. So basically, this just ensures that we have the closed forms are locally exact, so they don't have to be globally exact, but locally that's true. So that's the first thing to keep in mind. Now, Frobenius's theorem, or just Frobenius theorem. Now, what this just tells us is it gives us the integrability conditions, right? It allows us to know, like, when, it has to do with like uh, uh, finding integrability over submanifolds. Where is it? I don't feel like reading the whole thing, but it just allows you to have integrability for is at most p-dimensional. Yeah, so you're finding like p-dimensional subspaces. That's right, or submanifolds, whatever. Um, that's Frobenius' theorem. I'm being kind of hand wavy right now. Sorry, I'm a little rusty. Stokes theorem. So we kind of saw the hint at Stokes theorem earlier, but it should look something like uh, Stokes theorem. Oh man, it's really lagging. Uh, yeah, it should have appeared a little earlier. I don't know what's going on, but I mean, we got a glimpse of Stokes theorem. I mean, it's basically just that the integral. Um, did I, did I pass it? Because I want you guys, because there's two different formulations of Stokes theorem in this book. Um, at least that's what I remember when I was reading it. He decides to go through both of them. Um, yeah, I don't know what's going on here. Let's try Stokes. By Stokes theorem. Now it's only showing this one. That's weird. Yeah, I don't know. But anyway, Stokes theorem. I mean, basically, it just says that the measurement is going to demand that objects can integrate invariantly. So you'll have the Poincaré's lemma. You have the Frobenius theorem for integrability conditions, and then you'll have Stokes theorem. So that's nice. And differential forms are going to fill that role exactly. The differential forms are meant to be integrated over. So you'll integrate them over a manifold, specifically for exact, for closed forms, right? And you can take like p forms and just like be able to integrate them over and over again, over and over and over again, right? So forms are the natural objects that we integrate, but geometrically, the boundaries and the interiors are going to become dual to each other because of Stokes theorem, which I apologize, I can't find it, but and my thing is loading very slowly, but yeah, we'll just move on. But the local exactness versus the global obstructions, that's going to reveal the idea of these topological types of invariants as well, which are interesting to study. But determinants and alternating multilinear forms mature into differential forms and the full theory of integration. So it's a nice. This is a nice chapter to really consolidate the last two chapters of our study of space um, in terms in the geometric language. Now, I'd say the cohomology of the n-torus using angular forms is probably um, see if the cohomology of the n-torus is here. Hello. Yeah, I'm not going to rely on this search function anymore. I don't know. My control F is being weird. But also, this is kind of a weird. Um, the PDF itself is loading kind of weirdly. But yeah, basically you want to show the gap between local and global geometry itself, and topology can obstruct the existence of the global potentials, um, which you're choosing to whatever systems that you're choosing to define. Um, So even when you have like local conditions that are satisfied, you can get topological obstructions, and that appears, with de Rham cohomology, gauge potentials, the idea of the Earnhoff-Bohm effect, and topological invariance in field theories. So that's why it's important. Let's move on. Calculus, the variations, and let's go to the first instance of it. Right. Oop, that should be the first instance of it. Wow, what the hell? That's extremely annoying. Calculus variations. Oh, well, anyways, basically, calculus of variations is trying to define trajectories that are determined by field of lines rather than a field of vectors. So we're trying to get rid of. I mean, if you haven't noticed, we're trying to get rid of the notion of an arrow. That we use for pretty much this unphysical idea of some arrow that's like just a vector that describes some speed or whatever. We're trying to get it purely in terms of lines, um, and reduce to geometric ideas. So, what natural path, um, what determines a natural path in a curved geometry? That's really the essential question that we're trying to ask. And this is actually a pretty long chapter, I think. Yeah, calculus of variations. Here we go. All right. Calculation deals with the following question: given a function, differential curves in a manifold, find those curves where it achieves a minimum along all the curves, or extremizes, in some sense, that particular curve is extremizing from the landscape of possible curves that we could use. So that's what the calculus of variations is built for. Now, a natural path, in some, like, let's say you have a curved geometry here, a natural path, like, that we would want to, be able to solve for or be able to describe, um, is basically what we're trying to solve, and you'll see a bunch of uh, pictures like that. But they're basically the main mathematical structures that we're concerned with are variational principles and geodesics themselves, the paths themselves, or solutions, and the Lagrangians and Hamiltonians from physics. They start to have these abstract mathematical structures associated with them, and spaces that are interesting, as well as cotangent bundles and symplectic forms, and the dynamics of phase space itself in curved geometry. Now, the geodesic equations come from variational principles, and we can talk about something called the Legendre transformation. Uh, yeah, the Legendre transformation is nice because, uh, yeah, the map is called the Legendre transformation. So this is a very powerful idea because it allows us to describe the mapping from the map from space where we're just looking at the configuration space of some system where you have some coordinate and the coordinates velocities, um, or its derivation, and the momenta or some other variable itself. They're called the cotangent bundle, and you take a map from the tangent bundle to the cotangent bundle, and you should be able to say things about this as well to generate dynamics in a nice way that is dual to each other. So yeah, Legendre transformations, the existence of minimizing geodesics and conjugate points as well is also another, um, being able to know the spaces of solutions for those things that gets covered here. Um, yeah, geometry itself begins to generate the dynamics, and basically the mechanics and physics of what we're interested in. And so the motion emerges from an optimization problem. Essentially, that's what variational mechanics is all about. It's about finding a minimal. Uh, it's about finding. It's about extremizing an action essentially, and dynamics is revealed to as geometry. Um, the quadratic forms that we uh, use will evolve into Riemannian metrics and energy functionals as they take on geometric meanings. So that's like something to keep in mind as you transition from, um, yeah, it's basically as you transition from um, uh, like linear algebra type concepts in something like she loves linear algebra from the section on quadratic forms. Um, you should try to be anticipating as well, like how is this going to turn into Riemannian metrics given all of the ideas that we have about dynamics and the algebras that we've constructed to geometrically manipulate space itself, right? Um, so yeah, and then the continuous symmetries as well, like flows and invariance of geometric structures and conserved quantities. Those are also super important. And Hamiltonian mechanics, Liouville's theorem, phase space, and the geometric foundation of analytical mechanics. Pretty much all of these things get covered in the calculus of variations chapter. Let's move on to Lie groups. Lie groups also play a very important role in uh, they play an important role in defining the dynamics as well of spaces. Um, yeah, groups of automorphisms, of various structures that arise. So basically, defining really what is a continuous symmetry that is manifest geometrically. The Lie group itself is a differential manifold, so it is a manifold, but it is also a group, right? And then we define what a group is. That um, there's an inverse element, and then there's like an action, group action. Okay, so all of the basic stuff. And a group and a manifold, so that the map of G cross G onto G is differentiable, then G is a Lie group. Okay, so that's what a Lie group is. Um, so Lie groups and then Lie algebras as well. Yeah, so Lie algebras would be like the differential form of the Lie group. Yep, invariant forms. Let Lie be a group. Let G be a Lie group. She'll say that the differential form is left invariant and right invariant for all A and G. Omega 1 and omega 2 are left or right invariant forms. Omega 1 wedge omega 2. That's, in other words, uh, invariant forms is a subalgebra of the algebra of the forms. We should call the invariant algebra, and then the right invariant. Uh, yeah, so they're developing what a Lie group is. Um, Oh, and the Markov equations as well. These are structure equations for that are important to give us the constants of the structure of the group. So they're structure groups. Um, and tangent space, the tangent space of the identity. I can't remember if that was up here or not. Yeah. The tangent space of the identity of is the Lie algebra itself. So that's like kind of a really big result as well. So that's what gets developed here. Lie theorems and local algebra, the global group structure as well. So we get a bunch of theorems that develop this, but really this matters because global symmetry of your geometric space is completely encoded within local infinitesimal data, which is kind of insane to think about. Because the symmetry itself becomes the differential geometric object. And you can think about local commutators that reconstruct global structure. And if you recall from linear algebra, finite dimensional algebras become the infinitesimal generators of smooth group actions and flows. So, you know, the preservation of Lie brackets under smooth maps between manifolds is important. And to prove then that the algebraic structure survives the nonlinear transformations, that's kind of why it's kind of why Sternberg includes the preservation of Lie brackets under smooth maps. So, yeah, commutators and algebraic relations are intrinsically geometric, and Noether's theorem, gauge groups, representation theory, the geometric classification of symmetries, all of these things basically are birthed out of studying Greek Lie groups and going through Sternberg's survey, if you will. All right, now differential geometry of. Now we're going to study Euclidean space. You might wonder why, because we've been doing everything's been like kind of nonlinear and kind of weird, but basically, um, how we what we try to ask is how can curvature be detected intrinsically without reference to some random like ambient space, right? And the way that we do this is with things that we construct. Um, we are interested in the submanifolds of Euclidean space, so particular two-dimensional surfaces in E3, right? Something like that. Um, how can curvature be detected, right? That's the question we want to ask. And they answer. Sternberg answers this with Cartan, the idea of Cartan moving frames, structure equations, and he defines the idea of connection and curvature forms. I'd say the major results here would be Cartan's structure equations. So let's look at this. Oh, it just decided to do that, bro. That's crazy. Hello. Yeah. Cartan, where you at? Cartan's lemma. Yeah, so we have Cartan's lemma, and then yeah, the structure of a submanifold. So the method of moving frames was first introduced by, or first invented by Darboux and explored it into its fullest by Cartan. So, roughly speaking, set of all frames in Euclidean space whose first k vectors are tangent to this and orthogonal. Um, basically, we can think about this. It's an easy exercise to show that the natural differentiable structure, there is differential projection we shall call uh, pi phi. Oh, sorry, pi sub phi of this projection onto the manifold, right? So, or really, it's connection. Sorry, the canonical connection. That's what it's called. So, this will allow us then Cartan's lemma, just structuring the submanifold, the equations of structure for submanifold. We can then go to Gauss's theorem, Gauss's theorema. We keep for tradition, we call it the theorema um, uh, egregium because it's just that important. Gauss's theorema egregium. This one gets nicely talked about. But what happens here? Yeah, so what happens here is basically curvature is going to become measurable because it's defined by essentially sorry, I just lost my mouse. Where did my mouse go? The hell? Oh, it died. That's why. Great. Everything's going crazy today. But yeah. Anyways, so the phi is an immersion of an n-dimensional manifold M into into Euclidean space in n plus 1 dimensions. For each point on the manifold, we get a linear transformation. Then the exterior two form depends only on the or the space of exterior forms with that linear transformation of the tangent space or of the tangent space. This depends only on the Riemannian metric induced by phi. Okay, and that basically tells us that curvature is not bending into some higher space, but actually curvature itself is but a defect in the local distance and transport machinery itself. So, because transport itself is defined or allows us to describe the connection and everything. All right. So curvature is measurable, and it's an internal property of this Riemannian metric. So curvature is within that quadratic form that has evolved into the geometric description that we have built. Okay. Now, this also connects to Gram-Schmidt orthogonalization, right? If you go back to the linear algebra, that evolves into slowly, continuously varying orthonormal moving frames in Euclidean space. Now, the index of vector fields and curvature integrals also give you preparation for the Gauss-Bonnet theorem. So that's nice. I think that it's covered here as well in the thing. But basically, the link to local geometry with global topology is why Sternberg chooses to include these ideas for the index of vector fields and curvature integrals, and integrated curvature itself that teaches topological invariance, and you'll get this like in topological defects, monopoles and field theory, and invariance with different types of modern field theories as well. So let's move on to the next one, and this is actually the last chapter. It's called Geometry of G Structures. So yeah, here we go. Now, what's important about basically the whole thing about this section would be defining that there's a unique canonical connection on a Riemannian manifold that's torsion free. Now I just kind of gave you basically the answer to everything, but the question initially that I think this chapter is really trying to answer, mainly, or to keep in mind, is how can vectors at different points be compared in curved space? Right? That's the essential problem we need to answer, and so you need to define distinguished maps, which we call pi, onto M, and the main mathematical structures again that are defined are connections, parallel transport. The idea of covariant derivatives come back, curvature tensors, and the major results that we get in this chapter would be Levi-Civita. So yeah, the Levi-Civita connection, or the Levi-Civita theorem, which says again we get a unique torsion-free metric connection on the frame bundle. Um, and the Bianchi identities. Let's see. By the way, if I mess up anything, feel free to leave a comment. Because just for everybody to be aware. Yeah, the Bianchi identities. Yeah. Similar arguments we shall have as exercise as reader. We can obtain Bianchi's identity. So he's making you work for it. But the Bianchi identity just tells us that if we were to take there, it's basically a statement about torsion and curvature tensors, basically, and their covariant derivatives, how they transform. And the Bianchi identity is just kind of like this conservation type of geometric law, if you will, for intrinsic curvature. And then Gauss-Bonnet theorem. Well, there's Bonnet's theorem. Yeah. Uh, let's see. Let's go back to Bianchi. Yeah. Let's try to just kind of zoom up here. Yeah, I don't know. This is being weird. But basically, you have curvature as this it's basically the non-commutivity of parallel transport around these closed loops that we define, and the measurable failure of the space to be Euclidean itself. And so basically the Bianchi identities. So you have the Levi-Civita connection, right? And then the Bianchi identities are going to allow you to, in the tensor forms of the Bianchi identities, gives you that curvature itself is going to obey the intrinsic geometric conservation laws themselves, like I said, and that will teach you that geometry is self-constraining. It is an internal consistency that provides these powerful restrictions. And so the Einstein tensor as well is this conservation of of energy momentum, and gravitation really becomes space-time curvature. So that's basically what the motivations are for the subject. Let's just go back to the beginning. I think we can just safely go back to the table of contents and review everything again. But yeah, so you have that space itself. Algebra becomes manifolds and tangent spaces that give us geometric control over everything. And then we define measurements. Um, you know, Integral calculus. You know, uh, the manifolds will acquire the differential forms in integration. Pretty simple. Motion gets described by its measurement is generated by dynamics, variations, and symmetries, and then curvature. Um, the dynamics and symmetry will culminate in connections and the full theory of Riemannian geometry. Right here. So the achievement of this book again is conceptual, right? I would say Sternberg consistently. And there's the sequence, I guess, that he suggests. But I would just suggest going through the whole thing, just straight through. It's more It's more of a direct approach, I would say. Um, yeah, I mean Sternberg basically his idea is to um, consistently privilege invariant structures over coordinates. And this book will re-educate your reader to think directly in the language of derivations, forms, flows, and connections. And that's part of the reason why um, the way that it's developed is important for basically theoretical physics in modern math itself. So, you're going to finish not really relying on some artificial grids, but you're going to be equipped with structural vision from the mechanics, such as like symplectic geometry or gauge theory as connections on bundles, gravitation as curvature. These ideas are going to emerge very naturally once you get through the book, or as you go through the book, and as you anticipate it. And Sternberg doesn't really just teach differential geometry. He's going to provide you basically this nice observatory, if you will, from which the invariant architecture of modern math and your idea of physics becomes very clearly visible. All right. So thank you for watching. Sorry for all the random pauses and stuff. It was kind of weird. But I figured the people that are like, still watching this right now, they're probably just kind of going through the book with me, or got a copy of PDF online and just kind of following along um, and just enjoying the ride. So thanks for sticking with me, and I'll see you guys next time.